Hello, everyone. Welcome back. And last class or last video, we talked about the stock process. And in this class, we're going to continue and talk about ethos lemma. As I mentioned very early in the first video that ethos lemma basically tells you if you have a stochastic process and then you have a differentiable function of that stochastic process, then ethos lemma will tell you what the process of the function will follow. So here you have a gx. G is a function of x and t. X itself is a stochastic process. So we're looking here is, what process does G follow? So what is dg? From ethos lemma, if G is a once differentiable with t and twice differentiable with x, then dg has the following form. So basically, is the partial derivative of g to x times mu. Mu here is actually a function here. And the partial derivative of g with respect to t. And there's a strange looking thing here, which, this half of the second partial derivative of g times sigma square. And so then we'll have this dg dx sigma dz. So for people that have, calculus background, if you look, if this g is, if x is not a stochastic process, and g is a smooth function of x, and dg would just be this term, well, you wouldn't have this part, and times dt. Now, if x is stochastic, it's sensible, obviously, to have this part here, right? Dg dx times the sigma dz. But then, why do we have this second partial derivatives here? So this is where ethos lemma will stand out. Now, the reason for that, we're not going to prove this, but let's offer some explanation for this particular structure that we see on ethos lemma. So essentially, we have looked at and said that we have a dz here, which is a Wiener process. It's really in this form here, where epsilon t is a normally distributed with mean 0 and standard deviation square root of delta t. Now, well, for this thing here, for the entire thing, dz, for epsilon t is with a mean 0 and standard deviation 1 or variance 1. Now, we can see that dz, the change of dz, has a component that is related to the square root of delta t. Okay, so if you say do a Taylor series expansion on G, so dg here will then obviously partial derivative of G with respect to x times delta x, dg dt times delta t, and you normally would have dropped all the second order derivatives and any higher order than the first order here, as you shrink delta t and delta x to 0, right? Because they will go to 0 much faster, and you can, at the limit, they will disappear. But since delta z here has something that to the order of square root of delta t, then delta x squared will have a term that is in the order of dt. So when you shrink delta t to 0, this thing doesn't shrink faster than dt, and it is shrinking at the same speed or same order of magnitude with delta t. So that's where this part is coming from in the ethos lemma. So this one wouldn't shrink faster, wouldn't disappear. So you will it is at the order of delta t. So you have to combine with this dg dt here. So if you do that, so essentially, you can drop all the higher order terms, but this have second derivative with respect to x will still exist, and it's order of dt. So you combine them together. So this dg dx times dx would just be this term here plus this term here. And you get this dg dt dt, which is this term here, times dt. And you also have another extra term here, which shows up here. This is where rearrange, you'll get this ethos lemma here. Now, if you don't really remember this, you just try to do your Taylor's theory expansion. You can always recover that. So you do your Taylor's theory expansion, you'll remember this part there. Gets you the order of magnitude of dt, and you will come back to this. And then basically this is just a rearrange form of this thing here. So in case you don't remember, you can always derive that. And so you don't, as long as you know how to do Taylor theory expansion and drop higher terms, then you will actually be able to recover the form of ethos lemma. Okay, so let's stop here.